Welcome, learners. Today we're tackling a really foundational piece of physics. We've got this great chapter on electricity, and we're diving deep in the simplest starting point, the static case.
That's right. We're looking purely at electrostatics, so stationary charges or maybe charges moving very steadily.
It strips away a lot of the complexity, doesn't it?
It really does. I mean, the whole interaction between electricity and magnetism, the dynamics that vanishes when things aren't changing in time.
So Maxwell's equations, the full set, they get a lot simpler.
Dramatically simpler. The time derivatives, the parts that link E and B fields dynamically, they just go to zero.
Okay, so what are we left with? What are the core rules for this static world?
We end up with basically two key equations, two constraints on the electric field, E.
Right.
The first tells us about the sources of the field. It's about the divergence, nabla dot E. It basically says field lines start and end on charges.
Only on charges. Got it. And the second one?
The second one is about the circulation, the curl of E, nabla cross E. And in electrostatics, that's always zero.
No whirlpools, no circulating electric field.
Exactly. No eddies. It's a non-circulating field. And that fundamental property is what lets us build this whole electrostatic framework so elegantly.
So where do we start building? What's the absolute bedrock?
It has to be Coulomb's law. That's the starting point for the force between two static charges.
Okay. And what does it tell us?
Well, it says the force depends on the product of the charges, Q1 times Q2. And critically, it's inversely proportional to the square of the distance between them.
That 1 over r squared relationship, that seems to pop up everywhere in physics.
It's absolutely fundamental here. That specific relationship is key to everything that follows. We also need the constant, right? 1 over 4 pi epsilon naught.
Right, the constant of proportionality. Tells us the strength of the force in vacuum, about 9 times 10 to the ninth in standard units.
Yep, that's the one. And historically tied up with the speed of light, actually, but here it just sets the scale.
Okay, force between two charges. But what if you have, like, a whole bunch of charges scattered around? 5, 10, a million.
That's where superposition comes in. And it's beautifully simple.
How so?
The total force on any one charge is just the vector sum of the forces from all the other charges, calculated one pair at a time.
So charge A feels the force from B, calculated using Coulomb's law. Then it feels the force from C, calculated the same way. And you just add those force vectors together.
Exactly. You just add them up. Vector addition, point by point. The presence of charge C doesn't change the fundamental force between A and B.
That's powerful. But adding lots of vectors sounds tedious.
It can be, which is why we move from the idea of force to the concept of the electric field, usually written as E.
How does the field help?
The electric field E is defined as the force that would be exerted on a tiny positive test charge divided by the size of that test charge, force per unit charge.
So it describes a property of space itself created by the source charges, independent of whatever you use to measure it.
Precisely. It tells you how space is modified by the charges. We can calculate E for a collection of point charges, using that superposition idea vector sum again, or for charges spread out continuously, we integrate over the charge density, rho.
Okay, we have the field. Now let's bring in energy. If I move a charge around in this field, forces are acting, so work is being done.
Right. And here's another payoff from that 1 over r squared law. The electrostatic force is conservative.
Conservative.
Meaning the work done by the electric field when you move a test charge from point A to point B, it doesn't matter how you get there. Straight line, wiggly path, doesn't matter.
The network is identical, only depends on the start and end points.
Exactly. And if you go all the way around in a closed loop back to where you started, the total work done by the field is always zero.
Okay. If the work only depends on the endpoints, that suggests we can define something simpler than the vector field E to capture this energy aspect.
Yes, it leads directly to the electric potential. We often use the Greek letter phi for it.
Phi. And how is it defined?
Since the work only depends on the start and end points, we can say the work done is just the difference in a scalar value between those points. That scalar value is the potential energy per unit charge.
Potential energy per unit charge. So instead of a vector E at every point, we just have a single number, phi, at every point.
That's it. For a single point charge Q, the potential phi at a distance r is just Q over 4 pi epsilon naught r. Notice it falls off as 1 over r, not 1 over r squared, like the force or field.
And the superposition, how does that work for potential?
That's the real beauty. Potential is a scalar. So the total potential from a bunch of charges is just the simple algebraic sum of the individual potentials. Add up the numbers. Much, much easier than adding vectors.
That's a significant simplification.
Yeah.
Okay, so we calculate the scalar potential phi everywhere, which is easier, but we often need the actual force, the direction. How do we get the E field back from phi?
We use the gradient. The electric field E is the negative gradient of the potential phi. Mathematically, E equals minus nabla phi.
The gradient that tells you the direction of steepest descent, right? Like on a hill map.
Exactly. So the negative gradient tells you the direction of steepest descent.
So the E field always points downhill on the potential map, from higher potential to lower potential.
Precisely. It shows the direction of the most rapid decrease in potential.
And that relationship, E equals minus grad phi, that connects back to one of our starting points, doesn't it?
It does. Remember we said the curl of E has to be 0.
Yeah, no whirlpools.
Well, a fundamental mathematical identity is that the curl of any gradient is always 0. So if E is the gradient of some scalar function, minus phi in this case, its curl must be 0. It fits perfectly. It confirms mathematically that the electrostatic field is conservative, non-circulating.
Okay, that ties up the potential side nicely. Now, what about the other fundamental equation, the one about divergence to sources?
Right, that brings us to Gauss's law. And to understand that, we need the idea of flux. Electric flux.
Flux like flow.
Sort of. Imagine field lines radiating out from a positive charge. Flux is a measure of how many of those field lines pierce through an imaginary surface you draw in space.
Okay.
Let's try a picture. Imagine the charge is like a light bulb, or maybe something shooting out tiny particles radially in all directions. The density of these particles falls off as 1 over r squared.
Because they spread out over a bigger sphere as you go further out. Makes sense.
Now, put a closed surface around that source. Any Shakespeare, box, weird potato shape, doesn't matter. The total number of particles, the total flux, passing outward through that surface is constant.
Regardless of the surface's shape or size. Why?
Because if you make the surface bigger, the area increases, but the density of field lines decreases by just the right amount, that one-order dependence again. So the total number piercing the surface stays the same. It only depends on the strength of the source inside.
Okay, that's a key insight. What if the charge is outside the closed surface?
Then any field line that goes into the closed surface at one point must come out somewhere else.
So the inward flux cancels the outward flux.
Exactly. The net flux through the closed surface is 0 if the charge is outside.
Wow. Okay, so the net flux only depends on charges inside the surface.
Precisely. And that leads directly to Gauss's law. It states very simply that the total electric flux through any closed surface is equal to the total charge enclosed inside that surface, Q internal, divided by that constant epsilon naught.
Flux equals Q over epsilon naught. That's the second fundamental equation of electrostatics. It relates the field via flux to the source's charge.
It describes the divergence of the field, essentially. It's incredibly powerful, especially when you have symmetry.
Let's see an application. Say we have a big sphere with charge Q spread evenly throughout it. Finding the E field outside using Coulomb's law and integration sounds nasty.
It would be. But with Gauss's law, it's almost trivial.
How?
You draw an imaginary spherical Gaussian surface outside the charged sphere centered on it. Because of the symmetry, the E field must be purely radial and have the same magnitude everywhere on your imaginary surface.
Yeah.
Then Gauss's law just says E times the area of your imaginary sphere, which is 4 pi r squared, must equal the total enclosed charge, which is just Q, divided by epsilon naught.
So E times 4 pi r squared equals Q over epsilon naught. Rearranging gives E equals Q over 4 pi epsilon naught r squared.
Exactly. The field outside the sphere is identical to the field of a point charge Q located at the center. Symmetry plus Gauss's law gave us the answer almost instantly.
That's really elegant. Okay, last piece. Visualizing all this. Field lines and equipotential surfaces.
Right. Field lines are curves drawn so that the tangent at any point gives the direction of the E field there.
Yeah.
And how close together the lines are represents the field strength.
Denser lines mean stronger field.
Yep. And equipotential surfaces are surfaces where the potential, phi, is constant, like contour lines on a map, but in 3D.
So if you move a charge along an equipotential surface, no work is done.
Correct, because there's no change in potential energy.
For a point charge, we said the field lines are radial, pointing outwards or inwards. What are the equipotentials?
They're concentric spheres centered on the charge. Surfaces of constant or mean surfaces of constant phi.
And what's the geometric relationship between the field lines and these equipotential surfaces?
They are always perpendicular to each other. Always.
Why? Is that just how it turns out?
No, it has to be that way because E is the negative gradient of phi. The gradient always points in the direction of the maximum rate of change, which is perpendicular to the surfaces of no change, the equipotentials.
So the field lines, showing the force direction, are always perpendicular to the surfaces where potential is constant. That holds even for complicated charge setups.
Absolutely. Like for a dipole, two opposite charges, you get those curved field lines looping from positive to negative, and the equipotential surfaces are these sort of oval shapes surrounding each charge, always cut perpendicularly by the field lines.
Okay, putting it all together then. We started with Coulomb's law, the 1 over r squared force.
Which led, because it's conservative, to the scalar potential phi, related to the field by E equals minus grad phi. That also guarantees the curl of E is 0.
And then the other side was Gauss's law, relating the flux or the divergence of E directly to the enclosed charge, Qn over epsilon naught.
Exactly. Those two pillars, zero curl and divergence related to charge density, define the entire world of electrostatics. You've got superposition, the conservative nature, potential, the gradient relationship, flux, Gauss's law. That's the core toolkit.
It all seems to hinge quite delicately on that inverse square law, doesn't it?
It really does. The fact that the force is conservative, that we can even define a path-independent potential, stems directly from the 1 over r squared nature of the force.
Which leads to a final thought for you, our listeners. We saw how the 1r Kuhn law makes the work done around a closed loop zero, which is essential for defining potential. What if physics were slightly different?
Yeah, imagine the force law wasn't exactly 1r squared. What if it was, say, 1 divided by r to the power of 2.9999999?
Would the electrostatic field still be conservative? Could you still define a simple scalar potential the same way? What would break?
Something fundamental would change. Worth thinking about.
Definitely something to mull over. Thanks for joining us for this deep dive into electrostatics.